term use much better. So. Recitation will need to speak. So yes, if you're in recitation tomorrow, you will be expected to attend recitation tomorrow. Yeah. Good luck. Oh yeah. Socks? I don't know about socks. It's possible. It's possible. There's a room for that effect. Okay. What's that? Oh yeah. When you bring a recitation, I would bring a piece of paper to write things down on. I would say what I tell the CAs, I had a CA meeting this morning, what I tell the CAs is that the first thing the CAs are supposed to do in recitation is say, are there any questions? So you bring your questions to recitation, you bring a piece of paper to write down the things that you might learn in the problem solving, and get those taken care of. So your questions are the first things that the CAs are supposed to work on, and then they have things that they'll talk about with respect to problems. If you ask questions for the whole period, that's fine too. But your questions and getting your needs taken care of are the first priority of the recitation. Okay, yeah, thanks for asking. Yes, second. CAs will have office hours, and I'll have those posted on the schedule page. If you scroll down this page right here, what you will see is it says CA information to be announced. And they actually give me their office hours and everything. I should have that posted probably this evening sometime, and you can find out what they need with them. Keep in mind, and by the way, many times I get requests for tutoring and so forth. I'm happy to help you line up with a tutor, but I will tell you the CAs are free tutors during their office hours. Okay? So don't be afraid to go and ask them for assistance as if they were a tutor during their office hours, because that's what I'm paying them to do. Okay? If you need additional help or you want some other outside tutor, then of course I'm happy to help you get that as well. And I've got some excellent students who do tutoring in chemistry that happens for you, then of course let me know. Other questions? Good group. Should I call roll down? Yeah. Do I do any research going to? No, I don't. Actually, I teach and advise students. I got out of the research business about 20 years ago because I decided that what I really loved was teaching and advising students. And I feel extraordinarily lucky to be able to do what I do. And so I like that. That's why I like these first days of class. I like the interactions a lot. And so I don't do research. And I don't miss it. I tell you, the most wonderful thing I always do is sitting in the seats right out here in front of me. And that's pretty cool. So. That's everybody got wow, power here. Okay, well, let's dig in. If I don't get in your hands, I'm looking upstairs, I'm looking downstairs. Okay, I have open minds. The open minds are going to be filled with biochemistry. Now, as I said in the email I sent out to everybody last night, if you didn't get the email, then maybe you're not listed on the list on the Blackboard list very well. By the way, I don't get Blackboard, so you won't find, if you go looking for the course on Blackboard, it won't be there. You can go to the website I gave you here to find the class. I recommend in general downloading. I've got all the figures for the class available. I've got them available in PowerPoint and PDF formats, same files, and the outline. If you download that and you bring it in here, then you're not trying to quickly scribble down all of the notes or all the figures and so forth that I've given you. So you can write on the figures if you bring them to class with you. I think that is the best way to go. I see somebody over here who has already done that, and I strongly recommend that. I think it's the best way to take notes. Okay? If you go to buy the textbook and they provide all these things for the instructor's notes and all that, or the textbook notes and so forth to write on, you can have that as well. Okay? So I'm providing this to you. If you have used textbooks, you're basically going to see the same figures that they're going to provide in there. So I'll just talk about one of my CAs here. That's Jessica Morgan, who's sitting on the side. Jessica will be a CA for 2 of the recitation sections, and you will get to know her. Do I have CAs here? I don't see you when I have CAs. Okay. Well, let's talk about chemistry. When I think about chemistry, most people have the notion in their minds, well, we're talking about the chemistry of living cells. And the chemistry of living cells was where biochemistry had its roots. Okay? The idea that cells had chemistry going on inside of them is something we realized for a long time. And for a very long time, it was felt that chemistry that goes on inside living cells is really exotic. It's really very different than what's happening in the rest of the universe. Okay? And over time, people came to realize, and by the 1800s, people came to realize that the chemistry that was going on in living cells was no more exotic than the chemistry that was going on everywhere else. There are things that happen in living cells that don't happen anywhere else, but at the level of chemistry, that chemistry is, in fact, exactly the same. Okay? So that's the roots of biochemistry. The real modern roots of biochemistry date to about the 1930s. And in the 1930s, a man named Schrodinger had the rather radical idea that by the way, I'll just give you general information. You're welcome to take these notes if you want. You don't have to. I will also tell you one other thing, that you'll see a lot of structures this term. In general, I'm not going to require you to memorize structures, but I will tell you one of the structures that I think that you should memorize. Okay. So we'll get to that. So Schrodinger had the idea that the roots of biology were not in tissues, they were not in organisms, they were not even in cells. Okay. The roots of biology are in molecules. And that dates to the 1930s. So that was only about 75 years ago that we really came to the realization that there's a molecular basis of biology, and it's from that molecular basis of biology that the term molecular biology comes from. Biochemistry is at the root of molecular biology, because biochemicals are the molecules of molecular biology. Okay? Today we're immersed, absolutely swimming in information about molecular biology. Because upon that realization, our focus turned from understanding macroscopic things about biology. Why is it that I have this birth defect? Why is it that I have blonde hair? Why is it that I have no hair? Okay? These have their roots in genes, in chromosomes. Understanding this was very, very important to us. And so we turned our focus to that. By the 1950s, we understood exactly the structure of the DNA that gave rise to the healthy information of the genes. By the 1970s, we began to see much more at the genetic level what was happening with those genes, and by the 1980s, we began developing some incredible tools that allowed us to unlock the secrets of the DNA. Those secrets are contained in the form of the sequence of bases that are there. We are in what people now describe as the post-genomic era. The post-genomic era refers to the fact that once we had enough ability to determine the sequence of bases for an entire genome, it created a new science called genomics. In 2001, the outlines, the essentially finished version of the human genome became available for the first time. And to give you an idea of that, that may seem to you like, oh, that's just little historical facts, but to give you an idea about how fast things have happened in biology, there's not a science on the face of the earth that has had the revolution that biology has had in the past 25 years. When I was a graduate student here at Oregon State, I got my PhD at Oregon State in 1986. When I was a student here at Oregon State, the thought that we would have the sequence, the DNA sequence of any genome was unfathomable. 1986 was 23 years ago. Okay. One proposal for my PhD project was that I determine the sequence of the human gene. And I said, no way. Way too complex. Today, I can take any single one of you in this room and help you to clone that gene overnight. Okay? That's pretty phenomenal. We went from having very little ability to manipulate and understand DNA to being able to routinely determine sequences of millions of bases of DNA. Human genome sequence becomes available. It took something like several years to determine the first genetic sequence of about 80 nucleotides. Several years. Okay? The human genome, when we finally sat down and started doing it, took about 5, and today we can do a genome in probably a month. So there's been a revolution in terms of technology, there's been a revolution in terms of tools, and there's been a revolution in terms of our knowledge as well. Our knowledge is growing exponentially. Now, the bad news for you guys is that means that there's a heck of a lot more you got to know than what I had to know when I went through it. Sort of a joke, but okay. But the reality is there's a lot more information there. What I want you to know are the highlights of that information, the important things that you're going to take away from this class for your own professions, for the things that you're going to be ultimately professionals in. Okay, well, let's dive into this. The disease in the genome. As I said, there's no way today that you can pick up a newspaper and not see some medical advance every single day. I teach a class called Molecular Medicine. In that class, we have news of the week. And we get inundated in that class with the medical news of the week, just the things that were reported that week. It's because we have what I would describe as the renaissance of biology. The renaissance being that we have access to information like we've never had before. We can start putting different pieces of information together and understand how all these things are happening. What you see on the screen, of course, are chromosomes and representations of chromosomes, and chromosomes are at the root of information in biochemistry. We won't talk an awful lot about chromosomes this term. This term is more the sort of foundations of biochemistry. Next term, in DD 451, we will, for the last half of the term, talk in considerable depth about molecular biology. But before we talk about molecular biology, we have to understand the sort of roots of biochemistry, the chemistry underlying all of that, in order to go forward. Okay. Evolutionary timeline. We look at the evolutionary timeline, you see these in a variety of places. That evolutionary timeline puts us pretty late in the scheme, folks. We're not very long on this face of the earth, and hopefully we last half as long as the dinosaurs did. The tree of life. The tree of life breaks into three main branches, the three main branches being prokaryotic cells, eukaryotic cells, and archaean cells. We, of course, are eukaryotes. Eukaryotes are organisms that have a nucleus. They have organelles like the nucleus, like mitochondria, like the endoplasmic reticulum, and so forth. So that's what eukaryotic cells have. Prokaryotic cells, by contrast, are much simpler. They're what we refer to as the bacteria. And all prokaryotic cells are unicellular, meaning that they don't come together and clump together to make an organism. So all prokaryotic cells are unicellular. Some eukaryotic cells are unicellular as well. So we're an example of a multicellular eukaryotic organism. Yeast, on the other hand, are a unicellular eukaryotic organism. Yeast have organelles, they have nuclei, they have mitochondria. Okay. Archaean cells are the most recently discovered branch of the various kingdoms of life. And we won't really say much about them. I'll talk about them very briefly at one point in this term, but they are thought to be a much more primitive form of life, and they're actually fairly hard to cultivate, and so we don't say a lot about them. I will say a lot this term, however, about the difference between prokaryotes and eukaryotes. So when I use those terms, I want you to keep those things in mind. Bacteria and higher cells, that's what we're talking about. DNA, everybody knows that A pairs of C, G pairs of C, etc. Okay? They're the bases. There's all the information. Okay? You have 7 billion base pairs of these. Base pairs, of course, A pairs of C, G pairs of C, as I said. Okay? And these come together in ways that allow information to be passed from one generation to the next. Again, we'll talk more in detail about that next term. I don't think I need to talk about that. Okay? Yeah, so that's the basis of what I want to say with respect to molecular biology. What do I do now? Turn our attention to some basic chemistry. Common question I get in the class is, do I need to have organic chemistry? The answer that I give is it's a prerequisite for the course, but if you're willing to waste your money on taking it without having it, I'm willing to take your money. Okay? Now, I say that sort of jokingly, but I do let people in who have organic chemistry. And in general, I don't recommend taking the course unless you have organic chemistry. But I'll also say I don't teach this as a chemistry form of biochemistry. There's a lot of ways of teaching biochemistry. And there are some people whose foundation in biochemistry is much more chemical in nature, so everything they see is in terms of chemical reactions, et cetera, et cetera. We'll talk about chemical reactions this term. Okay? And we're going to talk about a few mechanisms of this term. But for the most part, my roots are not on the chemistry side of things, but more on the molecular biological side of things, the proteins, the DNA, the RNA, and so forth. That is to say that we shouldn't understand basics of chemistry. In freshman chemistry, you learn something, I hope, about hydrogen bonds. Hydrogen bonds arise from hydrogen bonds, and by the way, the things I'm now talking about, yes, you are responsible for. Hydrogen bonds arise from unequal sharing of electrons. Okay? In freshman chemistry, you should have learned something about electronegativity. Electronegativity is a measure of the attraction of the nucleus towards electrons. Okay? The higher the electronegativity, the more strong is the attraction of the nucleus for the electrons. If we compare the electronegativity of nitrogen with the electronegativity of hydrogen, what we discover is that nitrogen has a slightly higher electronegativity than does hydrogen, meaning that nitrogen pulls electrons towards itself more tightly than hydrogen pulls it towards itself. This pulls it towards itself. These are electrons that are being shared between nitrogen and hydrogen. One electron coming from hydrogen, one electron coming from nitrogen in this particular bond. If there's unequal sharing, that means those electrons are being pulled more closely towards nitrogen. It's not an ionization in which the electrons are completely given up, like we think sodium chloride, where chloride takes the electron and sodium loses the electron. But instead, it's the big kid, little kid with the spent lunch money, right? Actually, the big kid, little kid with the spent lunch money is more like taking the electrons. I take your lunch money and you're not going to have it back because I'm going to use it to eat them. Instead, the big kid, little kid is more like we're fighting over that lunch money. The little kid isn't that much liquid as the big kid. And that's the best I come up with on top of my head. Okay? Oxygen has a greater electronegativity than hydrogen does. Now, as a result of these partial sharing of electrons, nitrogen gets the electrons closer in, if you want to think about it that way, than hydrogen does. So nitrogen ends up being partially negative. That's what that little delta sign is there. Hydrogen ends up being partially positive. Well, these partial positives and partial negatives do, in fact, factor into electronegativity, because you can see in this case this partially positive hydrogen right here is attracted to this partially negative nitrogen over here, pulling them closer together. Plus attracts minus, right? It's actually this pulling between the partially positive hydrogen next to an oxygen in water that gives water the properties that it has. Water has a very high boiling point compared to other molecules of similar molecular weight. Okay? The molecular weight of water is 18. The molecular weight of carbon dioxide is 44. Yet at room temperature, water is a liquid, carbon dioxide is a gas.